Come on, my dears, let us proceed further in chapter number 7. Kindly read this statement of first illustration. Have you read it? Look, the circuit diagram, whichever they have given, the same diagram I have redrawn here. Now tell me, there are two PN junction diodes. One is D1, another is D2, correct? The resistance connected in series with this diode is 100 ohm and with this diode it is 400 ohm. Now these are the terminals A and B, between which there is a battery of 2 volt terminal voltage, correct? How much? 2 volt, fine. Now initially they have said in the first case that here positive terminal of the battery is connected at point A and here negative terminal of the battery is connected at point B, correct? In short, VA is greater than VB, correct? And then after they have reverted the terminals of battery. When you make connection in a reverse manner, then VB will be greater than VA, okay? Let us take both the cases one by one. First of all, VA greater than VB. In short, here terminal connected is positive and here terminal connected is negative. Okay, fine. Now tell me, for this particular diode, you know P with positive, P with positive, P with positive, N with negative. So this diode D1 is right now forward biased. That's what I am writing here. D1 is forward biased. But so far D2 is concerned, its P-type semiconductor is at negative potential and N-type semiconductor is at positive potential. P with negative, N with positive, so it is reverse bias. So diode D2 is reverse bias, correct? Fine. Now tell me, in this case, when this diode D2 is reverse bias, there won't be any current flowing through reverse bias diode because they have said in the statement, for reverse bias condition, the resistance is infinite. In this branch, if resistance is infinite, then no current will flow in this branch. At present, no current flows through this branch. Then whatever current starts from battery, positive terminal, that current will flow this way. That current will flow through D1 only, fine. It will not flow through D2, correct? And that current flowing in the first case through the battery, I am taking as I1. What is the formula for current for a single loop? Effective EMF divided by equivalent resistance. Effective EMF is between points A and B. That potential difference I am taking VAB, correct? And divided by equivalent resistance. Because current is flowing in this branch where I find resistance, series connection of these two resistances. Series connection of these two resistances. So effective resistance is addition of individual resistances. Come on, resistance of this diode in the forward bias condition I am taking RF1 plus this resistance they are given by symbol as R1, correct? I repeat, current formula is effective EMF divided by equivalent resistance, correct? Now this potential difference between terminals A and B, they have given in the statement as 2 volt. What about resistance of first diode in the forward bias condition? They have given in the statement 100 ohm plus R1. R1 they have given as 100 ohm. 100 plus 100 that is 200 and 2 upon 200 that is 1 upon 100 that is 0.01 ampere, correct? Fine. Now revert the terminals of battery. Now it is here negative terminal and here it is positive terminal. If here it is negative, then P with negative and N with positive, so diode D1 is reverse bias. Diode D1 is now reverse bias, correct? And here it is negative, here it is positive, So for second diode, P with positive, N with negative. So second diode is right now forward bias. Second diode D2 is right now forward bias. And you know, in case of reverse bias condition of a diode, they have given resistance as infinite. So now in this branch resistance is infinite. So no current will flow in this branch. And now this terminal is positive. So current will start from the battery this way and it will flow only through this branch. Correct? And that current flowing through the battery in the second case I am taking as I2. Come on, recall the formula of current in words for a single loop. Effective EMF divided by equivalent resistance. Effective EMF, here it is, come on, between points B and A, the voltage I am taking as VBA, VBA, that is effective EMF, potential difference between points B and A, because VB is greater than VA, correct? And now equivalent resistance in this branch, equivalent resistance in this branch, come on, diode D2 is forward bias, so equivalent resistance in this branch, come on, what is it? It is a series connection of these two, and in case of series connection, what is effective resistance? Addition of individual resistances. Come on, the resistance of this diode in the forward bias condition I am taking RF2 and this resistance is R2. Come on, this value they have given in the statement as 2 volt. What about RF2? Resistance of second diode in the forward bias condition they have given in the statement as 100 ohm. What about R2? R2 is right now 400 ohm. 100 plus 400, that is 500, and 2 upon 500 if you find out, answer is 0.004 that many ampere. If they ask this current in milliampere, you may multiply this ampere value by 1000. When you multiply this by 1000, it will become 4 milliampere, 4 milliampere. But unless and until asked in milliampere, you should not convert the value in milliampere, leave it in ampere only, and you know SI unit of current is ampere, correct? Leave it in ampere. They might have given in milliampere in textbook, but you don't see that, you simply find out current because they have asked current only, they have not asked the unit of current, correct? So we are better finding the unit of current in ampere, that is in SI unit, correct? So leave it in ampere only in short. Now kindly read this statement of second example, second illustration. Have you read it? Look. Come on, they have given part of one circuit this way. Here it is PN junction diode made up of silicon. Here it is PN junction diode made up of germanium. This point is E, and by mistake they have not given the potential at point E. Actually they must give, and that potential at point E I am showing by symbol VE, which they must give 10 volt, then only you will get the answer as per the textbook, okay? In the calculation they have considered 10 volt, but they have simply forgotten to mention it in the statement, in the figure. So please write here VE equal to 10 volt in the statement, okay? Fine. Now tell me, here is some resistance which they have given 1 kilo ohm. For kilo they have shown symbol capital K, which is very wrong. You must write small k for kilo, small k for kilo. And whatever is the voltage between the two ends of this resistance, it is right now output voltage, let it be VO, which we require to find out. Fine. Now, remember what is the barrier potential for silicon? In the PN junction diode made up of silicon, what is the barrier potential? It was 0.7 volt, and for germanium it was 0.3 volt. Now same barrier potential is given another name, it is called knee voltage. What is it called? Knee voltage. So what is knee voltage or barrier potential for this silicon diode? It is 0.7 volt, let it be VD1, and for germanium it is 0.3 volt, let it be VD2. So this barrier potential or knee voltage is 0.7, and this one is 0.3, addition comes out to be 1 volt. Now tell me, if barrier potential between these 2 points total knee voltage is 1 volt, then potential applied here must be more than plus 1 volt. Must be more than plus 1 volt. Then only there will be current through these 2 diodes. Then only this series connection will be in forward bias condition. If you apply here potential which is more than 1 volt, then both the diodes will be forward biased and they will allow current to pass through it. Okay? And we are given that potential here as 10 volt, which is greater than 1 volt. So because that VE value is greater than VD1 plus VD2, then really right now both the diodes are in forward bias condition, and in that case, come on, current will pass through both the diodes, and that current I am showing by symbol I. Okay, fine. You know this is the sign for showing this terminal which is grounded. This is grounded terminal. Okay, and for any terminal which is grounded, its potential should be taken 0. Fine. Now you just do one thing. You start from here, move in the direction of current till this grounded terminal, and you just calculate the changes in potential. Come on, here potential I am taking as VE, correct? VE. And when you move this way, you are going from positive to negative terminal, so potential will decrease. How much? Let it be VD1. So minus VD1. When you move from this point to this point, again potential will decrease, and then again you should write minus, let it be VD2. And when you move this way in the direction of current, whenever you move through the resistance in the direction of current, potential will decrease, so I should take the product I into R as negative. So I am writing minus I into R, correct? And because you have arrived at this grounded terminal for which potential is 0. Now just put up all the values. VE value, come on, they have taken 10 volt. Come on, VD1 is barrier potential or knee voltage for silicon diode, which is 0.7 volt. This is barrier potential or knee voltage for germanium diode, which you must remember it is 0.3 volt. Minus I as it is. What about resistance? Resistance value here I must put in ohm. What is given to me? 1 kilo ohm. 1 kilo ohm is 1000 ohm. Okay, and that equals to 0. Find out I from here, you will get answer 0.009, that many ampere. Okay, and what about output voltage now? It is voltage across this resistance, which is nothing but current into resistance. Current into resistance, correct? Current is, come on, 0.009 ampere. What about resistance? It is 1 kilo ohm, which is 1000 ohm. This multiplication is 9 volt, correct? So this is the output voltage, 9 volt. Got it? Now we go further in the theoretical part. We have to study about Zener effect and Avalanche effect. Let us see both the effects one by one. First of all, we are talking about Zener effect. Zener effect. Mr. C. E. Zener had found this effect. So in his memory we call it Zener effect. Now what is that? Last time we had discussed about reverse bias condition of PN junction diode, correct? And in that we had also seen reverse bias characteristics. And in that graph you must have remembered, when we increase reverse voltage beyond a certain limit, then what happens? Majority of covalent bonds are getting broken, releasing very large number of electron hole pairs, and there is a sudden rise in the current. Okay, this is the phenomenon which is known as breakdown of PN junction diode. This is called breakdown of PN junction diode. Now this breakdown you can have in practice in two different manners. In one, it is just occurring very fast, suddenly, briskly, at once, and in that we are going to see Zener effect. And if the breakdown takes place slowly, stage wise, say sequentially, gradually, then we are going to see about avalanche effect, correct? Any breakdown which is occurring suddenly at once gives rise to Zener effect. and if the breakdown is occurring slowly, gradually, then it gives rise to avalanche effect. Let us see one by one. First of all, we are concentrating on Zener effect. If you want to observe Zener effect, then amount of impurity added in the PN junction diode must be very large. If you add large amount of impurity while preparing PN junction diode, then you will observe Zener effect. Look how. When we add very large amount of impurity, what we find, the depletion layer is obtained very narrow. If depletion layer is very narrow, then inside the depletion layer, electric field will be very strong, because electric field strength formula is equals to potential difference V divided by perpendicular separation, correct? E equals to V upon D. If width of depletion layer is very small, naturally the strength of electric field will be very large. For example, if the reverse voltage is say 2 volt, and if the width of depletion layer is suppose 200 angstrom, converted into centimeter, multiplied by 10 raised to minus 8, then this electric field strength comes out to be 10 raised to 6 volt upon centimeter, or 10 raised to 8 volt upon meter. 10 raised to 8 volt upon meter. Now this is very strong electric field. Now because of this very strong electric field persisting in the PN junction diode, specifically in the depletion layer, you know what does it do? Because of application of very strong electric field, it so happens that in the depletion layer, majority of covalent bonds are getting broken almost at the same time, correct? Say simultaneously. If there is a simultaneous breaking of majority of covalent bonds, naturally all of a sudden you will have release of very large number of free electron and hole pairs, correct? And as soon as free electron and hole you have in the depletion layer, you know what will happen? Free electrons will be getting accelerated in a direction opposite to electric field, whereas holes will be accelerated in the direction of electric field, correct? In short, what will happen? That very large number of free electrons will take part in the conduction of electricity, and along with that the bound electrons also will join, correct? In the direction opposite to motion of hole, you can think of bound electrons. In short, both the electrons, whether it is free electron or bound electron, both of them will move in a direction opposite to electric field. And because of very large number of free electrons and very large number of bound electrons, you will have very large amount of reverse current, and that reverse current is called Zener current, and this very effect is called Zener effect. Here I am showing you the graph of current versus voltage, graph of current versus voltage. See, this is reverse current and this is reverse voltage, IR versus VR, okay? That graph is this, look here, correct? Now tell me, till this limit of reverse voltage, what happens? The current, reverse current is very small, of the order of microampere, and it remains almost constant, which we call reverse saturation current, reverse saturation current. But then, when reverse voltage is increased beyond a certain limit, what happens? Just now I explained, because of Zener effect, you are going to have very large current, and that too very briskly, very suddenly, you will get sharp increase in the value of reverse current. So there is a very sharp increase in the reverse current, and that I am showing by such a graph. Okay, fine. Now tell me, this voltage, this minimum reverse voltage at which this breakdown occurs, it is called reverse breakdown voltage, shown by symbol VR, and it is in this case known as Zener voltage. What is it called? Zener voltage. Fine. In case of this Zener effect, the reverse breakdown voltage is found to be less than 4 volt, less than 4 volt. Let us summarize all these points for Zener effect. As I said earlier, for observing Zener effect, you need to have more amount of impurity in the preparation of PN junction diode. So I am writing amount of impurity is more, and because of more amount of impurity, what happens? depletion layer is found to be narrow. When depletion layer, width of depletion layer will be less. That's what I am writing here. Width of depletion layer is less. And because width of depletion layer is less, then electric field is very strong. Electric field is very strong, correct? And then majority covalent bonds break almost simultaneously. Majority covalent bonds break almost simultaneously, giving you sudden increase in the reverse current, and that minimum reverse voltage at which this breakdown occurs is known as reverse breakdown voltage, shown by symbol VR. For Zener effect, that minimum reverse voltage or reverse breakdown voltage is less than 4 volt. Okay, and a PN junction diode in which breakdown occurs through Zener effect is known as Zener diode, correct? Fine. Now let us see another effect which is called avalanche effect. What is that avalanche effect? I am showing you. Say, if you keep amount of impurity less while preparing PN junction diode, then in case of less amount of impurity, what happens? Depletion layer is found to be very wide. So width of depletion layer is more. If width of depletion layer is more, then electric field will be weak. That's what I am writing here. Width of depletion layer is more and electric field is found to be weak. At that time what happens? That opposite to direction of electric field, some of the electrons which are liberated from the covalent bonds might be broken out of thermal energy absorbed from surrounding, correct? And because of that, whatever number of electrons are freed in the depletion layer, they will be first getting accelerated in a direction opposite to electric field, correct? Might be electric field is initially weak. Now when electric field is weak, initially less number of electrons whichever are freed will get less amount of acceleration. But when they are accelerated in a direction opposite to electric field, they happen to collide with other bound electrons which are engaged in the covalent bonds. And when they strike with them, they may knock them out. And if they do so, the number of freed electrons would be more. And same number is now getting accelerated in a direction opposite to electric field. So again, more number of electrons will strike more number of more number of bound electrons in the covalent bonds, releasing further large number of electrons. This is how successively, gradually, correct, ton by ton, the number of freed electrons goes on increasing. And then as the number of freed electrons, number of freed charge carriers are going on increasing, naturally it will give you rise in the reverse current, but not sudden rise, it will be gradual rise in the reverse current. This very phenomenon is known as, this very effect is known as avalanche effect. What is it called? Avalanche effect. And here, whichever PN junction diode undergoes breakdown through avalanche effect is known as avalanche diode. What is it called? Avalanche diode. In case of avalanche diode, breakdown occurs at reverse voltage greater than 6 volt. Greater than 6 volt. I am showing you everything in the figure now. Look. In case of avalanche effect, when this reverse voltage is increased beyond a certain limit, what happens? The weak electric field initially accelerates the electrons, whichever small number is there, it is getting accelerated. And as it is getting accelerated in direction opposite to electric field, it will gradually release more and more electrons from the bonds, correct? And then if more and more number of electrons are freed from the covalent bonds, that will increase the reverse current gradually. So you can see this reverse current increases gradually, correct? Here in both the cases, remember, initially the current is of the order of microampere, later on it is obtained very large of the order of milliampere. But here the rise in the current is sudden rise, very sharp increase in the current, and here there is a slow increase in the current. This sharp increase in the current takes place almost at the same reverse voltage, and here there is some little range of reverse voltage over which this current goes on increasing gradually. Fine. So here this some sort of very sharp angle is there, and here the curvature is not very sharp. Okay, fine. Now, just look at these points, just summarize all the points. Come on. Here we have kept amount of impurity less, and because of less amount of impurity, the width of depletion layer is more. When width of depletion layer is more, electric field will be weak, and then covalent bonds are breaking gradually in sequence, correct? Giving you slow increase in the reverse current, correct? This very effect is called avalanche effect, and any PN junction diode in which breakdown occurs through avalanche effect is known as avalanche diode, in which this reverse breakdown voltage is found to be greater than 6 volt. Okay. Now, in textbook they have written this sort of note, just kindly remember. If reverse breakdown voltage is less than 4 volt, it is purely due to only Zener effect. If a reverse voltage is between 4 and 6 volt, the breakdown may be partly due to Zener effect and partly due to avalanche effect. So, there is effect which is produced as a mixture of these two effects, Zener effect also and avalanche effect also. Fine. But in practice, all these diodes in which breakdown voltage is either less than 4 volt or between 4 and 6, in short, a PN junction diode in which breakdown occurs might be partly due to avalanche effect, partly due to Zener effect, or solely due to Zener effect, that all diodes are called Zener diodes, correct? A PN junction diode for which the reverse breakdown voltage is less than or equal to 6 volt are called Zener diodes. So, we will call all these diodes as Zener diodes. But if reverse breakdown voltage is more than 6 volt, then we call it avalanche diode. What do we call it? Avalanche diode. Because there the breakdown is occurring due to only avalanche effect, correct? Then we will call it avalanche diode. Now onwards, our discussion will be limited to Zener diodes. Okay? So, let us see what is the circuit symbol for showing Zener diode in the circuit. Here is a circuit symbol for showing Zener diode in the circuit. Earlier we had used the same symbol for PN junction diode also. The only change is you are supposed to show this vertical line segment, not simply vertical line segment, but you must show this extended parts this way. Okay? When you show extended parts this way, this becomes the circuit symbol for Zener diode. But remember, Zener diode is always employed in the circuit in reverse bias condition. So, anode is at negative potential and cathode is at positive potential. P with negative, N with positive, so it is reverse biased, correct? Fine. Now, let us see the use of Zener diode as a voltage regulator. Use of Zener diode as a voltage regulator. Fine. Now, the same characteristic I have shown here also. Once again, this is reverse bias characteristics for Zener diode. And this particular reverse voltage at which breakdown occurs, it is called reverse breakdown voltage. Sometimes we call it Zener voltage, shown by symbol Vz. And as I said, it is less than or equal to 6 volt. For a typical Zener diode, let it be 5 volt. Okay. So, this voltage value I am just going to take 5 volt as per the textbook. Now, tell me, here we find very sharp increase in the current. Initially, this current is of the order of microampere, later on it becomes of the order of milliampere. Have you noticed one thing? Though current may increase or decrease, there may be large change in reverse current, but that large change in reverse current occurs at the same constant voltage. Then you may have a question, though voltage remains constant, how current goes on increasing? See, current I is equal to V upon R according to Ohm's law, correct? So, I is no doubt proportional to V, but I is also inversely proportional to R. Here what happens in case of Zener effect? Majority of the covalent bonds are getting broken, and if you have got sudden rise in the number of charge carriers, then conduction of electricity would be very fast decreasing the resistance. So when I is proportional to 1 upon R, I is inversely proportional to resistance. When resistance will decrease, current will increase. That's why though voltage is constant, then also current is increasing because of decrease in resistance. Got it? Fine. Now this same property we utilize in preparing one voltage regulator circuit using this Zener diode. How? I am showing you. Consider this circuit diagram in which this is the resistance connected in series. Let it be shown by symbol RS. This is series resistance. Here is symbol for Zener diode. Come on. Here is anode and here is cathode. Fine. And here is load resistance or resistance of that electrical component for which you require this regulated voltage. Whatever constant voltage you get, you want to apply that voltage to some component. That component has got some resistance. Let it be RL, which we call load resistance. And here potential difference between these two terminals is called output voltage. Correct? Let us see now. The input voltage I am showing by symbol VI, which is unregulated, which is varying. It is not constant. And now that unregulated voltage, we have to transform it into regulated voltage. Here one condition is required. Let this input voltage change, no problem. But in any case, it must remain greater than Zener voltage. Fine. Now tell me. Here this Zener diode is to be employed in the reverse bias condition. So anode must be at negative potential and cathode must be at positive potential. And now current starting from this terminal, correct, away from positive terminal, this current I am taking as I. This current will come up to this junction. Further it will be divided into two parts. Part of the current flowing through Zener diode, let it be IZ, and remaining part is flowing through load resistance RL, let it be IL. Correct? Now tell me, summation of these two will be equal to I. Correct? Now tell me, just apply Kirchhoff's second law here. If you apply Kirchhoff's second law in this loop, then according to that law, voltage applied should be equal to summation of voltages obtained. What is the voltage applied here? It is VI. Correct? And that should be equal to summation of voltages obtained. What is the voltage obtained across RS? It is current into resistance. So it is I into RS. Plus remaining voltage you get between these 2 points, and it is the voltage across Zener diode, which we know it is going to remain constant, equal to Vz. So this Iz into whatever is the resistance of the Zener diode, that product will give you total voltage between these 2 points. Let it be Vz. So I am writing plus Vz. Correct? Now tell me, here RS is constant, correct? This resistance is constant, and so far voltage across Zener diode is concerned, it is also remaining constant. Fine. So this RS is constant, Vz is constant. What does it mean? If input voltage will increase, then it will cause increase in this current. So current I will increase. If input voltage decreases, then this current will decrease. So this input voltage may change. Depending upon that, this current will change. But so far Vz is concerned, Vz is remaining constant. So potential difference between these two terminals will remain constant. And you know, the voltages across components connected in parallel are always equal. If here voltage is Vz, then here also voltage will be Vz, and same will be the output voltage. So output voltage in this case is equal to Vz, and Vz is how much? It is 5 volt constant. Right? So this unregulated input voltage you have transformed into regulated voltage. Because this circuit does the job of regulation of voltage, we call it voltage regulator. Okay. This is how Zener diode can be used in a circuit called voltage regulator. Fine. Now we go for light emitting diode. Light emitting diode, shortly written as LED. Fine. This is a special PN junction diode which converts electrical energy into light energy. Fine. Now, how it converts electrical energy into light energy, I am showing you. Look, here is PN junction diode prepared out of non-carbonic semiconductor like gallium arsenide, okay, fine, having large amount of impurity. We just keep amount of impurity very large in a special PN junction diode prepared out of non-carbonic semiconductor like gallium arsenide, fine. Here in both the amount of impurity is very large, fine. Here is the junction and here I am showing you depletion layer. So, this much is width of depletion layer, fine. Now, we just keep this PN junction diode in forward biased condition. So, N with negative, P with positive, okay. Now, tell me, what will happen now? Electrons will flow this way. When electrons are flowing this way, you can think of electric current in just opposite direction, fine. So, electric current is flowing this way. Now, tell me, actually here electrons, free electrons move from N to P type semiconductor this way, correct? Now, tell me, in N type semiconductor, which are the majority charge carriers? Negatively charged free electrons, but they have very high energy because they are in the conduction band. And when they enter here and when they associate with the holes in the P type semiconductor, but where are holes? Holes are in the lower energy band, which is valence band. So, whenever any electron is entering from N to P type semiconductor and combining with hole in P type semiconductor, then remember, actually it is making transition from higher energy level to lower energy level. So, when it is making transition from higher energy band to lower energy band, naturally its own energy will decrease. Then question arises where that energy has gone. That energy in this case gets transformed into light energy. That energy is getting transformed into light energy. If you take a simple PN junction diode, normal PN junction diode, then in that also electrons, when they migrate from N to P type semiconductor, at that time also energy of electron decreases, but that energy is getting transformed majority into heat. Whereas in this type of semiconductor, which is made up out of gallium arsenide and having large amount of impurity, it so happens that loss in energy of electron is transformed into majority into light energy, fine. And because you have kept amount of impurity very large, there are large number of free electrons in the conduction band, large number of holes in the valence band, and so large number of free electrons will make transition. If large number of free electrons are making transition, then there will be great amount of decrease in the energy of electron, and that is why we will have production of more light energy. So, if you want intense light to be emitted, then you should go for using such a PN junction diode, correct? Fine. Now, here whichever light emitting diodes are emitting visible light, in that the minimum band gap energy is observed to be 1.8 electron volt, 1.8 electron volt. Have you noted one thing? We have kept amount of impurity quite large, and because of that what will happen? Large number of free electrons will make transitions from conduction band to valence band, and so there will be more loss of energy for electrons. If loss in energy of electron is more, then we will have production of more light energy. That is, you will have emission of light with more intensity, okay. Brighter light can be emitted out of this construction, okay, fine. And because it emits light rays, I just show light waves this way getting emitted from this construction, and its circuit symbol is this. You know circuit symbol for PN junction diode, it is this, and because light is emitted, we just show light rays emitted this way, okay, going outside, away from this. Got it? This is the anode, this is the cathode. Remember, light emitting diode needs to be always forward biased, N with negative, P with positive. Got it? Fine. Now, what can be the maximum wavelength of light emitted from LED? Come on, its formula is Hc upon Eg. Hc upon Eg. What is Eg? It is band gap energy, and what is it? the difference in energy between lowest energy level of conduction band and highest energy level of valence band. It is called band gap energy. And tell me why this lambda is maximum here? Because this energy is minimum. Why this energy is minimum? Because you are taking difference in energy between two closest energy levels, in one in conduction band, one in valence band, correct? Because this value is minimum, this has to be maximum. Okay. What are the advantages of using LED? There are three advantages mainly. Come on, it can be operated at low forward voltage. This forward voltage we require very low. Then it has very long life. It is estimated to be around 20 years. Around 20 years. So it's a very long life. And using this LED, we can have very fast switching operation. On and off switching operations can be made possible very fast using this LED. Okay. Then where are LEDs used? Light emitting diodes are used in, remote control, then in on-off indicator. Whenever our TV, in the drawing room, whenever our TV is in the standby mode, you must have observed some red colored lamp is kept on, which is very small. It is nothing but light emitting diode. Okay. So it is used as an on and off indicator. Then it is also used in display board. In many of the restaurants, you must have observed the display board mentioning the menu items, correct? And that scrolling is made, and actually it is inside the which circuit? It is the circuit using this LEDs only. Then optical communication, about which we will discuss the things in detail in the next chapter, and also in the decorative lights these LEDs are used. Okay, fine. Now let us go for photodiode. Photodiode. It is a normal PN junction diode only, but it is connected in always reverse bias condition. Always in reverse bias condition. Come on. The normal PN junction diode, we just show it this way, and because it is connected in reverse bias condition, come on, N with positive. N with positive, come on, P with negative. So it is reverse bias. Fine. Now here what we do, we just keep some transparent window, and on which we just make the light incident. When you make light incident on that transparent window, it so happens that that light falls on this depletion layer. On this depletion layer, light is falling. Now what will happen? Tell me. Already at room temperature in the depletion layer, there are certain number of covalent bonds getting broken, correct? But now, because of absorption of incident light, it will so happen that more number of covalent bonds will get broken. If more number of covalent bonds are broken, it will release more number of pairs of electron and hole. So if more number of electron hole pairs are produced, generated, then you can say it will increase number of charge carriers. If it will increase number of charge carriers, then here, because this circuit is in reverse bias condition, reverse current will increase. Because of release of more number of charge carriers, come on, reverse current will increase. Fine. So here we get reverse current in a direction from positive to negative this way. Correct? This is the flow of that reverse current, and just to measure that reverse current, we have connected here one current meter in series, that is microammeter. Okay, fine. And here symbol for showing photodiode in the circuit is this symbol, which is the same as symbol of PN junction diode, but in addition to that, you must show light energy which is getting absorbed. Here light rays are going away from this symbol, here light rays are just shown to be shown towards this symbol, correct? Here inward and here outward, got it? Fine. Now here, if you do not make the light incident, then also in the reverse bias condition, very little reverse current is flowing. It is known as dark current. It is known as dark current because it is obtained in the absence of light. In the absence of light, so we call it dark current. Okay, fine. Here, in order to have more reverse current, the energy of one photon of incident light must be greater than band gap energy. Energy of one photon of incident light is given by this formula, Sc upon lambda, where lambda is the wavelength of incident light, that must be greater than band gap energy. Okay. If you show this by symbol capital E, then E must be greater than Eg. E must be greater than Eg. Okay. Remember this condition for the detection of light using photodiode. We will use this condition in one of the numerical. Okay. Fine. When these incident photons have energy more than band gap energy, then it will break more number of covalent bonds and releasing more number of charge carriers, and then more number of charge carriers take part in the conduction of electric current. Naturally, reverse current will increase. That's what I am writing here. Reverse current is increasing. Tell me here, which energy is converted into which energy? Light energy is converted into electrical energy. Come on, light energy is converted into electrical energy. This principle is opposite to principle of LED. Principle of LED was to convert electrical energy into light energy. It was conversion of electrical energy into light energy. Here it is conversion of light energy into electrical energy. Got it? Fine. Now, where are these photodiodes used? They are used for these fields. Come on, optical communication, about which we will study the things in detail in next chapter. Then they are also used in CD player, also used in computer and in security systems. Okay. In the optical communication, in the CD player, in the computer and in the security systems. Okay. Please remember these fields where these photodiodes are used. Let us discuss now one more special PN junction diode called solar cell. Solar cell. It is a source of EMF. How? I am showing you. In the figure you will find the construction of a solar cell. How it is made up. I am showing you. Look, we have one normal PN junction diode, but here we keep a P-type semiconductor in the form of very thin layer over the N-type semiconductor. Above this N-type semiconductor, we have very thin layer of P-type semiconductor, and between these two semiconductors we have, come on, extremely narrow region called depletion layer, which is around the junction. Okay. So this region, just take it as a junction right now. This is P-type semiconductor in the form of thin layer, and this is having thick layer. It is N-type semiconductor. Fine. Now tell me, above this P-type semiconductor and below this N-type semiconductor, we have metallic electrodes. This particular electrode in contact with P-type semiconductor is called anode, correct? Which gets positive potential. How? I am showing you. And this electrode, which is also metallic electrode, which is kept in contact with N-type semiconductor, it is called cathode, which has negative potential. Now the voltage between these two terminals here obtained is, practically we find approximately 0.5 volt to 0.6 volt. How? I am showing you. See, above this we have transparent layer through which light can enter in this PN junction diode. Okay. Now, if we use here if we use this anode in the form of continuous metallic sheet, then it will simply cover entire P-type semiconductor. We don't want that. We don't want to cover the P-type semiconductor completely. For that, what we do? We keep anode with a specific shape. What is that specific shape? Specific shape is like this. It is not complete metallic sheet. It is having shape like this, in which this is metallic strip, and attached with that strip are some 4-5 metallic wires. And because these wires can be compared with our fingers, we call this anode as finger anode. One finger anode is kept on left side, one finger anode is kept on right side. That's why I am showing this shaded part as anode, but it is not continuous the whole metallic sheet? No, is not like that. Otherwise, it will cover up this p-type semiconductor completely. We don't want that. We want to keep this part of p-type semiconductor exposed to incident light. We want to keep it open to incident light. That's why we arrange this sort of finger anode in this construction. Okay, come on. So here is a finger anode. This is the metallic strip. These are the metallic wires, and one such anode is here. One such anode is here. Okay, come on. Now, when the light is made incident, what does it do? Through this transparent layer, it will enter. And because layer of p-type semiconductor is very thin, almost no light energy will be absorbed, and without any much dissipation of, without any wastage of energy, we will have almost same incident light energy to be incident on this depletion layer. Now, what it will do now? You know, inside the depletion layer, we have covalent bonds. At room temperature, some covalent bonds are getting broken on average, but that number is very small. Now, with the absorption of this light energy, more number of covalent bonds are broken. And if more covalent bonds are broken, it will release more number of charge carriers. You will have more number of electron hole pair, correct? Now, how EMF is generated, I am showing you by this figure. The same PN junction diode is shown here, correct? Say this is N-type semiconductor, this is P-type semiconductor. Now, when this light energy is falling, with the absorption of incident light energy, in the depletion layer, you will have more breakage of covalent bonds, releasing more pairs of electron and hole. And now tell me, in the depletion layer, there exists electric field from N to P-type semiconductor this way, correct? So, as soon as any electron is freed, it will be getting accelerated in a direction opposite to this electric field. And so far holes are concerned, they will start moving in the direction of electric field. Ultimately, what will happen? Whether it is a bound electron or free electron, they will move this way, opposite to this electric field, correct? And so here you will have accumulation of electrons, and if you have accumulation of electrons, accumulation of negative charges, it will give rise to negative potential. But this is negative with respect to this, so this must be at positive potential with respect to this. In short, between these two ends across PN junction diode, we have some potential difference. That potential difference itself is known as EMF. But this potential difference or this EMF generated here, it is called photovoltage. What is it called? Photovoltage. Here it is, photovoltage. And practically we find this photovoltage of the value nearly 0.5 volt to 0.6 volt. 0.5 volt to 0.6 volt, correct? Now tell me, once you have EMF here, you can use that EMF. Suppose I want to run some electric bulb using this EMF. Then I should connect that bulb over here. Whichever component you are connecting here, it has got some resistance which is going to consume this electrical energy. That resistance I am showing by symbol RL. It is called load resistance. It is called load resistance. And if you connect here some bulb or some load resistance, then you know current is flowing from positive to negative this way. This current flowing through load resistance I am showing by symbol IL. So ultimately you will have this absorbed light energy converted into electrical energy, correct? So what is the principle of working of this solar cell? Conversion of light energy into, come on, electrical energy. Conversion of light energy into electrical energy, correct? Here are written conversion of light energy into electrical energy. Got it? Fine. Then here the value of photovoltage depends on the intensity of incident light, because if you increase this intensity, then more number of photons are made incident. If more number of photons are made incident, naturally more number of photons will be absorbed. If more number of photons are absorbed, releasing more number of free electron and hole, then naturally if number of charge carriers goes on increasing, naturally you will have more current, correct? And you will have more production of photovoltage. So as intensity of incident light increases, this photo voltage goes on increasing. Fine. Then through which materials these solar cells are prepared? In practice, we find they are prepared from silicon, they are prepared from some other non-carbonic semiconductors like gallium arsenide, then cadmium sulfide, then cadmium selenide. Out of these non-carbonic semiconductors, these solar cells are prepared. Fine. Then you must remember certain points while preparing such solar cells. First, it must have small band gap energy. It must have small band gap energy. Then you know what will happen. If band gap energy is small, then compared to that, amount of energy of incident photon would be more. And if E is greater than Eg, then what will happen? More number of charge carriers will be released and giving you more amount of electrical energy. Correct? Fine. Come on, that band gap energy here we find roughly 1 electron volt to 1.8 electron volt. Okay? It should not be more than that. Then this material must have more capacity of absorbing light energy. Correct? More absorptivity for light energy. These materials must have more absorptivity for light energy. Then it must have more electrical conductivity also. Correct? Then only if the conductivity is more, then only there will be fast and easy movement for these charge carriers, and then you will have production of more photovoltage. Fine. Then the materials used in making this solar cell, it is called raw material. That raw material should be easily available. Then only over entire world right now these solar cells and solar panels are used maximum. Then what is called solar panel? What is called solar panel? See, if you require desired photovoltage, then you need to use more than one solar cells. When you connect more than one solar cells in the form of series connection, might be in the form of parallel connection, or might be mixed type of connection, that whole source of EMF is known as solar panel. In short, solar panel is a mixed type of connection of more than one solar cells. They might have been connected in series, might be in parallel, might be mixed type connection. Correct? A collection of more than one solar cells connected is called solar panel. Fine. Using this solar panel, what you can do, you can just charge, come on, secondary cell, you can just make it charge up during the daytime, and then overnight you can use the energy. Correct? During the daytime you can make it charge, and then during night time you can again reuse it. Okay? Then you know very much the application of solar panel in solar water heater as well as in solar cooker. Correct? Fine. What about uses of solar cell? Uses of solar cell. You know, in calculators you have solar cell, using which even in the absence of external battery we can run the calculator because of solar cell. Then we have solar cell, solar cell supported watches also. So in the watches also we employ solar cells, and cameras also. Okay, just to give you a flashlight. Fine. Now kindly read the statement of illustration number 3. Read it? Come on. For detection of incident light, which is made incident on the transparent window of a photodiode, you know, just now I told you about the condition. This condition must be satisfied. Energy of one incident photon must be greater than band gap energy. If energy of one incident photon is greater than band gap energy, then only the incident light can be detected. Okay? As such, we cannot see the light. So we cannot come to know whether light is really made incident on the window of a photodiode or not, because light is invisible. Then how to detect the presence of light using this photodiode? How I am showing you. Come on, band gap energy at present they have given 2.8 electron volt. 2.8 electron volt. Convert electron volt into joule. Multiply by 1.6 into 10 raised to minus 19. Correct? Then this multiplication comes out to be 44.8 into 10 raised to minus 20. That many joule. What about energy of photon of incident light? Energy of one photon of incident light is given by formula E equals to HF, where F is C upon lambda. F is C upon lambda. Come on, what is H? Planck's constant, 6.625 into 10 raised to minus 34 joule into second. C is the velocity of light in vacuum, 3 into 10 raised to meter per second. This is wavelength of incident light. You are given 6620 nanometer. Convert it into meter, multiply by 10 raised to minus 9. And now simplify. This value comes out to be 3 into 10 raised to minus 20, that many joule. Now just compare these two values. Come on, 10 raised to minus 20 here also, 10 raised to minus 20 here also. But here the multiplier is 3, here multiplier is 44.8. Because 3 is less than 44.8, we can say E is less than Eg. E is less than Eg. When E is less than Eg, come on, this condition is not satisfied. If this condition is satisfied, if E is greater than Eg, then only the incident light can be detected. But because this condition is not satisfied here, on the contrary, we get E less than Eg, then incident light cannot be detected. Okay, this would have written here, given light cannot be detected using this photodiode. Okay, my dears, I just forgot to mention about two very small points in this short note on solar cell. First point is that, see, in photodiode also we make the light incident, correct? And there also light energy is converted into electrical energy. Here also we are making light incident, and here also light energy is converted into electrical energy. Then what is the difference between photodiode and this solar cell? The difference is that in case of photodiode, we require external battery. But here in solar cell, we do not require any external battery. Got it? So I have written here, come on, external battery is not required. External battery is not required. Okay? And one more point, see the circuit symbol of solar cell. Circuit symbol of solar cell is this. You must write here A for anode, come on, where positive terminal of the battery is shown, and the negative terminal of the battery, actually it is not battery, but this is the EMF which is been generated. For this EMF generated, this is the anode, this is the cathode, and this is the light which you are making incident on the solar cell. Okay, these arrows must be inward. Got it? This is the circuit symbol for solar cell. Okay, thank you.